Hello everyone, I'm Shujun Zhang from University of Wollongong. It is nice to meet you online and welcome to join the Ferro Talk webinar tutorial. Today I will give a tutorial on why relaxor-PT single crystals possess giant piezoelectricity. Before I talk to that, I just show here is a milestone map for the development of piezoelectric materials. The first piezoelectric material is the quartz crystal, which was reported by Curie brothers in 1880. And the first ferroelectric crystals is rotor salt crystals, reported by Joseph Walasek in 1921. And then the first milestone ferroelectric ceramic is barium tantalite with perovskite structures, which can be poured to be piezoelectric active. And this material is first studied and reported in late 1940s by the scientists from United States, Germany, Soviet Union, and Japan. And later on, another milestone is a ferroelectric solid solution system, where the perovskite and member lead zirconate and lead tantalite they have high miscibility and form a morphotropic phase boundary, separating rhombohedral and tetragonal phase. Near the morphotropic phase boundary, they show very high dielectric piezoelectric properties. This solid solution was reported in the 1950s by the scientists in Japan and the United States, especially Bernie Jeffy and Hans Jeffy and Berlin Count. They did a very good, extensive, detailed job on the PZTs. Then in the 1961, another category perovskite structure, lead magnesium niobate, was reported by the Soviet Union scientist Dr. Smolinsky. And we can see, compared to barium tantalite, the PMN, we can see it's different because on the B side, there is a magnesium and niobate occupies the same crystallographic position. That means it's showing different behavior as a classical ferroelectric DP. This leads to a long-range disordering and a short-range ordering. Because of this, it shows a unique frequency-dependent dielectric maximum that is diffused or smeared Curie point. We call this material is a relaxor. So analog to the PZT solid solution, relaxor also can form a solid solution with PT, and they also show morphotropic phase boundary showing higher properties. Particularly important is some relaxor PT system can be easily grown into single crystals, like PMN-PT and PMN-PT. They showing very high strain, high piezoelectric coefficient, and high coupling factors. They first reported in early 1980s, and then I just show the main player before the year 2000, including Igor Park, Tom Schlott, Jun Kawata, Kenji Uchino, and Shikoro Nomura, Hosu Luo, Zhou Guangyi, and Zhang Yamashita, and some other scientists. So in recent years, in our group, we also find a doped PMN-PT crystal showing the double the value as a pure crystal. We just I will discuss later, reported by Dr. Fei Li, Jun Luo, and Tom Schlott. We can see from these figures, we can see for almost 140 years development of piezoelectric materials, the piezoelectric coefficient up to 3 orders higher than quartz crystals. So in order to observe the advantage of relaxor-PT single crystal more intuitively, we just compare the single crystal compared to the state-of-the-art PZT polycrystalline ceramics. These two figures showing the general trend, general observations for polycrystalline ceramics. We can see with higher Curie temperature and lower D23. For our single crystal, it's showing ultra-high piezoelectric coefficient far above the general trend. And also electromechanical coupling factor also about 90%, much higher than most of the polycrystalline ceramics. Meanwhile, the relaxor-PT single crystal showing a very high strain, about 1.5%, 5 to 10 times the strain of the piezoelectric ceramics. This is a revolutionary property improvement, since this is also lead to a question. Yeah, so why the relaxor-PT single crystal possess giant piezoelectricity? The first mechanism trying to understand the large piezoelectric strain and high piezoelectric coefficient in relaxor-PT crystal is from Igor Park and Tom Schlott in 1997. So they just showing the 001 pole room hydro relaxor-PT crystals. For room hydro crystal, the spontaneous polarization is along 111 directions. And these 111 directions, the angle between 111 and 001 direction is 54.7 degrees. So when we plot the crystal, they show only 4 degenerated domain exist. The others it disappeared because of domain reversal. Because it's a domain engineering configurations. For these domain configurations, if we apply electric field, we can see the 111 spontaneous polarization will rotate to along 001 directions because it's a stage 1. And this stage 1 corresponding to the electric field induced strain here, the piezoelectric coefficient almost about 2500 picometer per volt. And in this stage 1, only polarization rotation occurs. There's no domain wall involved. With further increasing the applied electric field, the 111 direction spontaneous polarization will switch to 001 directions. We can see here, there's a phase transition because the 001 direction is a spontaneous polarization direction of the tetragonal crystals. So in this way, this is a phase transition from rhombohedral to tetragonal phase transition. This is stage 2. Stage 2 corresponding to the strain behavior is here. There is a strain jump near the phase transition. Above this phase transition go to the tetragonal phase, the strain slope is very low. That means corresponding to the D33 is only less than 500 picometer per volt. So in this stage 2, there is not only the polarization rotation occur, also have the domain switch, and the multi-domain go to the single domains domain state. So later on, so Matthew Davis, as a PhD student in EPFL, guided by Dragan Damojanovic and Navasetter, they studied extensively about the engineer domain configuration in relaxor-PT crystal. We can see based on different phase and different polling directions, we can have very different domain engineering configurations, and we can get different properties. Then later on in 2000, Dr. Fu and Dr. Cohen, they first proposed a polarization rotation concept and its contribution to the high piezoelectricity. They use the first principal calculation focused on the 001 poled rhombohedral barometantanic crystals. And there are different rotation paths for the polar vector from 111 direction rotated to 001 direction. They found they have the A, B, C, D, E path, and they have the A, F, G, E path. They have different paths. Then this figure shows the energy as a function of spontaneous polarization directions. They found at low electric field for the A to F and A to B. For first principal calculation, they found the piezoelectricity along this path is 5 times higher than the along the A to B path, because A to F path is showing much flatter free energy profile. This will lead to a structural instability, and they will accelerate the polarization rotation, accounting for the high piezoelectric properties. In the similar time, so people think, use a higher order Dawson thermodynamic analysis. They found the monoclinic field also can be existed in relaxor-PT single crystals. And also they found MA and MC existed by the experimental measurement using the synchrotron or neutron scattering. They found the MA and MC is in the space group C, M, and PM. Meanwhile, Dr. Dwight Wieland, he reported that the observed monoclinic phase can be an adaptive phase, as a polar rotation inside the monoclinic phase is very critical for the high piezoelectricity. Here we only discuss the polarization rotation. Actually, the polarization extension. This is polarization rotation and this is polarization extension. Polarization extension also very important. However, for the polarization extension only occur at the temperature-driven ferroelectric to paraelectric phase transition. That means for the ferroelectric material is on the proximity of the Curie temperature. That means even the polarization extension can give a very high piezoelectric properties, but the temperature instability is so bad, so it's not good for practical applications. Later, Dragon just proposed a new phase diagram. For here, you can see this MPB region. Yeah? It separates the polar, and non-polar phase. And for this one, inside the MPB region, there is a solid dot far below the Curie temperature. For here, represent compositions here. MPB composition benefit from the polarization rotations, the polar to polar change, and same polarization rotation because of polar to non-polar change. That means they benefit from both the polarization rotation and the polarization extension. So this system is expected to show you very high piezoelectric properties. Then another one, another mechanism to explain the high piezoelectric property, the relaxor-PT, is anisotropic characteristic because it's a crystals. For anisotropic features, so in the crystal, the anisotropy free energy profile determines the easy paths for polarization change and corresponding to the enhanced properties. This figure shows the anisotropic piezoelectric D33 in room hydro with PMN-PT crystals. We can see that for room hydro crystals, the spontaneous polarization is 111 direction. From this figure, we can surprisingly find along the spontaneous polarization 111 direction, the D33 is only 100 pH per Newton, very small. The largest piezoelectric coefficient is of the spontaneous polarization. It's very close to the 001 direction. So D33 go up to 2300 pH per Newton. This is very high, showing very strong anisotropic characteristic. And this phenomenon also can be confirmed by the electric field induced strain. We can see along the 001 direction, the strain is very high. When we rotate away from the 001 direction, the strain go down drastically. So how to explain this? From this figure, from this equation, we see the apparent piezoelectric coefficient in the poly domains is related to the single domain piezoelectric coefficients like D15, D33, D22, and D31. D33 in room hydro single crystal, single domain crystals, the D15 usually is about 2000 pH per Newton. D31 is around minus 30, and D22 is about 500, and D33 about only 70. So we can see for the apparent D33 in poly domains is mainly attributed to the thickness shared piezoelectric coefficient D15. And then because of this, based on thermodynamic approach, Dragon discussed the origin of the high share piezoelectric coefficient in ferroelectric materials. The phenomenological calculation confirmed the properties enhancement is in the phase transition regions. That means when the compositions approaching to the MPB, we can see the energy profile greatly flattened. This MPB region is very flat, so it might makes the polarization rotation much easier, and this will induce very high piezoelectric coefficient. However, let's see the above mechanisms, including morphotropic boundary, anisotropy features, engineer domain configuration, they cannot explain why relaxor-PT exhibits much higher piezoelectric response when compared to other MPB ferroelectric materials. This table shows the relaxor-PT crystal with MPB compositions, and we compare to PCT crystal and with MPB composition. Both are crystals, so we can take advantage of domain engineering configuration. We can take advantage of the anisotropic characteristic, and they also have the MPB region. So compared to this, certainly we don't have the PCT crystal sample to measure the real properties. So this value is calculated by Hong in 1989. You can see the dielectric constant and piezoelectric coefficient is much higher than the PZT for relaxor-PT crystals. So what the difference exists here? Because above mechanism including MPB or domain engineering configuration, it doesn't consider the specific microstructure characteristic of relaxor-PT crystal, that is polar nano region or local structure heterogeneity. So dot cross, based on this characteristic dot crossing, we can regard this relaxor-PT as a 0-3 nanocomposite. That means the polar nano region is a 0-dimensional connectivity, and the matrix is a 3-dimensional connectivity. We can consider it a 0-3 nanocomposite. So this is a question. Do the polar nano region contribute to the high piezoelectric coefficient? Okay, yeah, for this figure showing a schematic about polarization rotation, we represented as a theta 1, and the shear deformation of the whole system, we represent as theta 2, and the transverse applied electric field. The theta 2, the shear deformation is related to the thickness shear piezoelectric coefficient D1 So the theta 2 corresponding to the D1 From this equation, we can see is related to the dielectric constant. Yeah, the dielectric constant is related to the polarization rotation. If the rotation, the theta 1 is larger, the dielectric constant go higher. That means higher piezoelectric coefficient. Meanwhile, the transverse acoustic mode related, when it becomes softer, it induces a larger elastic compliance. That means the elastic softening. Meanwhile, so that means for the piezoelectric coefficient, it relates to the dielectric constant, related to the polarization rotation, and the elastic compliance related to the transverse acoustic mode, and also the coupling between the polarization rotation and the transverse acoustic mode. So for transverse acoustic mode, they can be confirmed by neutron inelastic scattering reported by Dr. Guangyong Xu, that the existent polar nano region will softening the transverse acoustic mode. That means the existent PNR can increase the elastic compliance. They already confirmed about the neutron scattering. So the question is, if the existent polar nano region can promote the polarization rotation, then increase the dielectric constant. Here, in 2016, Feely studies phase field modeling in Leng Qiongchen's group at Penn State. And so he just treated the relaxor-PT as a 0-3 composite, and then we picked up the tetronal phase as a matrix, the spontaneous polarization along 100 directions, and the PNR, and the phase is orthorhombic phase. The spontaneous polarization is along 110 directions. So, and the 100 port ferroelectric PNR composite here, the orthorhombic polar nano region only exists along 2 directions. One is 110, the other one is 110. When we enlarge the polar nano region here, you can clearly see each polar nano region involves many lattice. Yeah, here, many lattice. This is 110 and 110. So, and particularly important is that there is polarization here, polarization discontinuity or string discontinuity. This will induce interfacial energies. And this interfacial energy includes the electrostatic energy, elastic energy, and gradient energy. Meanwhile, the polar nano region has its own Landau energy, which will maintain itself as a orthorhombic phase. The Landau energy and the interfacial energy, they will compete each other, and finally they lead to a flattened local energy profile. This will facilitate the polarization rotation. So in this figure, we can see the interface here. The interface, the color, and here, the color is different from the polar nano region, although different from the matrix. That means the computation of the interfacial energy and Landau energy, they will facilitate the polarization rotation nearby. Sorry. How to go back? Okay. So again, we use phase field modeling to just simulate the dielectric constant as a function of temperature. First, we only consider the orthorhombic PNR, the dielectric constant like this one. If we only consider the tetragonal matrix, the dielectric constant behave like this. So then we consider, we treated the relaxor-PT as 0-3 composite. We consider both the tetragonal matrix and the orthorhombic PNR. The dielectric constant is like this, exactly the same as the experimental observations. We can see the dielectric constant here is have a large increment at the cryogenic temperature. It's about 50 to 80% of their room temperature. Based on these equations, the piezoelectric coefficient also should follow exactly the same trend. And this large jump at cryogenic temperature is a cornerstone of the piezoelectric high piezoelectric coefficient at room temperature. So in order to further clearly explain the origin of the high piezoelectricity in relaxor-PT crystals and how the local heterogeneity or PNR impacts the piezoelectricity, we use the variation of Landau energy profile for an orthorhombic PNR and the applied electric field 100 directions as a function of the electric field magnitude. So the electric field, the driving electric field mimics the driving force for PNR rotations. And this is related to the interfacial energy and the Landau energy computation. That means that if interfacial energy going up, larger than Landau energy, the driving force go up. So now let's see what's the Landau energy development. We can see here, at the beginning, we thought applied electric field. The orthorhombic polar nanoregion have two stable state. One is 11 bar O, the other 110. We can see if without electric field, if the polar nanoregion will rotate from one stable state to another stable state, it needs to overcome large potentials. If we apply the electric field, that means the driving force going up, and because the computation of the interfacial energy and the Landau energy, the potential going down, decreased, and it makes the polar nanoregion rotate easier. Is much easier. Particularly important is at some specific electric field, because the interfacial energy and the Landau energy they compete and they flat the local free energy profile is very flat. So the polar nanoregion is so easy to rotate from one state to another state. Yeah. It's very easy to find. However, it should be noted here. When the driving force is exceedingly high, the polar vector of the PNR is routed to 100 directions and stabilized here. So this making the polarization rotation path is steeper, is a potential well. Here, the polarization rotation is harder and it's just stable in 100 directions. That means when the interfacial energy is too large and compete the Landau energy. So the system is not orthorhombic PNR anymore, it's go to the tetragonal side. So based on this, here it is worth it to compare this study with the earlier report on phono studies by Dr. Guangyong Xu. Phono studies shows that the PNR and phono interaction can induce a phase instability. They soften the transverse acoustic mode and increase the elastic compliance. In our model here, it is proposed that PNR facilitated the polarization rotation and enhance the transverse dielectric, but the computation of the interfacial energy and the Landau energy. These are energy computation, locally energy computations. So in order to verify this mechanism, we added the rare earth dopant on A side to replacing the lead here. Yeah. So we induce a rare earth samarium on the A side replacing lead, to then we induce a local random field being responsible for more relaxor component in relaxor-PT system. We grew the single crystal samarium doped PMN-PT single crystals, and we found the crystals should possess the dielectric constant and the piezoelectric coefficient and the electric field induced strain almost double the value of the PMN-PT crystals. Based on this, we just also use this high angle annular dark field stem with collaborate with Brodick and Labue from NC State. We found, as expected, the samarium dopant only go to the A side. It will not go to the B side. Meanwhile, the dopant on A side will greatly fluctuate the lattice parameters and induce the local tetragonality. So that means the dopant on A side will induce more local structural heterogeneity or polar nano regions, as our motivation expected. Now we already explained the questions. Why relaxor-PT single crystal possess giant piezoelectricity? It is attributed to the domain engineering configuration, take advantage of strong anisotropic of the crystal and the polarization rotation concept. It's also attributed to the very important structural instability. The structural instability can be induced by the morphotropic phase boundary, and also most important, it can be induced by the local structural heterogeneities, that means the PNR. So with this, I would like to conclude my tutorial and take questions. Thank you very much.